Hey everyone, Mr. Shatter here to talk about modeling and optimization. Objectives for this video to maximize and minimize functions using derivatives. First up, a nice little strategy for solving these max-min problems, complements of your textbook. Take a quick read. First up, example 1. Find two numbers whose sum is 20 and whose product is as large as possible. So we're going to go ahead and attack this the same way we normally do. We're going to let x equal the first number, and we're going to let 20 minus x equal the second number. So I know now that their product is equal to x times 20 minus x. We'll call that p of x, p for product. And then p prime x, which is the derivative, is equal to, well, I can just actually distribute the x. This is 20x minus x squared. So the derivative is simply 20 minus 2x. I know that's always defined, it's never undefined, so if I want to maximize, I need to set it equal to 0. So if I set this equal to 0, I could factor out a 2, and I get that x must equal 10. So if x is 10, then the other number, the second number, is 20 minus x, which is 20 minus 10, which is 10. This is the second number. So we'll just say equals, and so therefore the numbers are 10 and 10, and that would maximize the product. Okay? Example 2, inscribing rectangles. A rectangle is to be inscribed under one arch of the sine curve. What is the largest area the rectangle can have, and what dimensions would give that area? A picture is actually provided here, which is nice. You're not always going to be given a picture. In this example, let's talk about what we know. First of all, we know that this distance is exactly pi, because we know sine of 0 is 0, and then sine of pi is 0. Again, that's when sine comes back to cross the x-axis. So if I call this distance x, and I also know that this distance is the same, this is also x, then I can conclude that the base of the rectangle is pi minus 2x. All right? Additionally, I can conclude that this point right here has an x-coordinate of x, and a sine or a y-coordinate of sine of x, right? Whatever that value is if you plug it into the problem. And then I can also conclude that this value right here has an x-coordinate of pi minus x, but a y-coordinate of still sine x, because I know that the height is the same for points P and Q. So it's still going to be the same value of y. So I think I have everything I need to construct the area of my rectangle. All right, let's go ahead and make a formula. We use pink. Area, we'll call a of x, is equal to sine of x, which is the height of the rectangle, times the base of the rectangle is pi minus 2x, right? Base times height. This is the base. This is the height. There's one thing to note. In this example, I would have a restriction here. Restriction. And a lot of times in these max-min problems, there's always kind of like an understood restriction. In this problem, x would always be assumed to be less than pi, because if x was bigger than pi, you couldn't fit a rectangle underneath it. And it's always assumed to be greater than 0, because you wouldn't want to have a 0 or a negative distance, because you're talking about a value that's, you know, this distance has a positive value, so you wouldn't want to be negative. Can't be 0 itself, otherwise it wouldn't exist. It wouldn't actually be there. So that's my understood restriction that I'll need to consider as I move forward. Let's go ahead and see if we can take the derivative of the area. So the area function, this is just a simple product rule. So it'd be first function times derivative of second, is just -2, because pi is a constant, plus second function times the derivative of sine, which is a positive cosine. Positive cosine. Now there's no way to actually solve this algebraically, so I'm going to need the help of my calculator. But I can conclude that it's always defined. So I think the only critical points could occur when the derivative is equal to 0. So a prime x is equal to 0 when x equals, and now I'm going to ask help from my trusty calculator, Calci. I'm going to turn in Calci. We got to get, there it goes. And I'm going to input this in my derivative. So sine x times -2 plus pi minus 2x times cosine x. Always remember that your calculator should be in radian mode, and it looks like it is. And then we can do a little zoom trig action, which is number 7. A great thing to use when you're looking for trigonometric functions. All right, this thing looks nice. I have to ignore these negative zeros because I know my restriction is 0 to pi is x. So I'm going to ignore those. I have two to choose from, like right here and right here. And I know actually, interestingly enough, I have to ignore this one because I know that a change in the derivative of negative to positive would result in a minimum area. I'm trying to maximize the area. So I need to look at this 0 in particular. That's a change in the derivative from positive to negative. Let's go ahead and find that 0. So second calc, 0. We're going to go left bound, so maybe like right here. Press enter. We're going to go to the right of it, and then we'll come back and do a little guess. And it tells me that the 0 is 0.710. 0.710. Okay, now there's a few things that the question asks for. Specifically, number one is what are the dimensions that produce the maximum area? So I could go ahead and find that. I know that the base is equal to pi minus 2x, and so then I can roughly calculate the base of this rectangle. I'm just going to back out for a second. I'm going to do pi minus 2 times, what did we say, 0.710. And I'm going to get an answer of approximately 1.722 units. And I know the height is equal to sine of x, which will be approximately the sine of, what was it again, 0.710, and that is equal to approximately 0.652 units. And then I know approximately I could multiply these two values together, so we'll just multiply this one by 1.72159. That's enough. And we get an approximate area. So area is approximately 1.122. And so this information is the largest possible rectangle we could produce under those constraints.